What a beautiful greenhouse. I should be putting a picture of our greenhouse up in there. We're going to talk more about light. We're going to talk about light, we're going to talk about colors, we're going to talk about transparent and opaque. Transparent. Transparent is the light can go through it. That makes sense. Transparent. You're like, no duh, Mr. Blank. All right. And then opaque is the light can't get through it. Now, it seems like no duh, but remember, we have other light to think about than just visible light. You're like, I know about transparent. Give me an example of something transparent. Bing, a window. Water, good. Something opaque, a wall. All right, so windows and walls. But that's just thinking about visible light. What about that whole other spectrum we just talked about, radio waves and so forth? Is a wall transparent or opaque to radio waves? Is a wall. Can radio waves go through the wall? Well, my radio still works in here. So yes, your cell phone still works in here. It can communicate with the cell tower outside the wall. So this wall, we would say, to radio waves, see, we have to identify the type of light. To radio waves, that wall is transparent. So that wall is opaque to visible light. I can't see outside right now. To visible light, it's opaque, but to radio waves, it's transparent. You have to go through things list by list there. If I look, well, let me show you, let's do this. Let's do it by colors. So I have here red, and here they are, green and blue. Look here, red, here's blue, here's green. I don't know what this will look like. We could do it this way. It might work. If I take this blue guy, I put it over the camera lens. I hope this works. Let's see. Yeah, this will work. All right. When I go like this, is the grass still green? Now you know it's green. Your brain knows it's green. What if I do this, red one? Is the grass still green? So what we're seeing here, when I do this, when I put this over here, this red is transparent to some things and opaque to other things. It's transparent. What color does it let through? It lets red through. But it doesn't let green through. It's opaque to green. So as the green tries to get from the projector, but it can't get through this piece of plastic, it filters it out. So this is opaque to green, but transparent to red. And then this blue lets the blues through, but not the greens and the reds. So we're going to watch blues, reds, and greens. I have a green one here. This one's kind of frosted. This one will let greens through, but not let, let's see. Doesn't work as well through the camera, but it lets green through, but not reds and blues. So what we got to do is we got to treat each frequency, each wavelength, each color, each type of light differently, and then say, well, through this, is it transparent and opaque? Well, what about through this? Well, what about through this? Each one. Let's keep going. Now we got all these questions here. Let me just put them all up because it's hard for me to swipe without participants. Okay. Opaque materials get warmer because the light doesn't go through. It dead ends. So the light has a choice. When it can't go through it, when it can't transparent its way through, it's got to either bounce off, reflect, or get absorbed and turn into heat, thermal energy. If it can bounce off, well then great. Then it can keep on staying light. If it gets absorbed, now it's heat. That's why. All right, transparent object, window, water, sure. Look, is this sunscreen? Does sunscreen let ultraviolet light through? Does sunscreen let ultraviolet light through? Some, sure, but it would be opaque. It would be opaque to ultraviolet light. I know it's transparent to visible light. Why is it transparent to visible light? Because when I put it on, you can see through it. You can see me. Ultraviolet light can't get through, but regular light can and do the regular light things. But ultraviolet gets blocked, or at least mostly blocked. So we take each thing in turns. Can you get, here, let's get this next one. The question's coming up. Can you get a sunburn through the windows? Can I get a sunburn in the greenhouse? Do I need to put on sunscreen when I go in there? No. Because guess what? That roof in the greenhouse is, well, to visible light, it's transparent or opaque. Well, it's transparent because I can see through it and the plants can receive the light. But to ultraviolet light, I'm not getting sunburned. So it must be opaque to ultraviolet light. You see what you got to do? You got to treat each light and each object it's trying to get through individually. You can't just say walls are always opaque. Some lights can go through walls. All right. We'll skip that question. You can pause at it and look. All right, if you really want to look, pause. Otherwise, I'm pushing. All right. Let me click all these up. Is this the one where? All right, we kind of hit a lot of these as we were talking. So I'll pause and look at that to make sure you understand. Okay. Now we're going to talk about reflection. With reflection, the energy hits, bounces off, and it keeps going. This is called mirror. It's called regular reflection. You can see yourself in it. There he is, giving a mirror high five. And you can see the object come right back off at you. Here's my daughter Sammy. Now let's talk about diffuse reflection. So this was regular. So I take this mirror. Here, let's take a look at you. Hey, there you are. See that? See yourself? This is what you look like to me right now. I miss you so much. Okay, this is regular reflection. It's a mirror. Now if I take this aluminum foil, and you kind of see this is regular reflection. Maybe you see yourself a little bit. And then I take it, and it's not perfect, right? I got some bumps in it. The bumps redirect the light. Think about why this is not perfect reflection. But now I crumple it up. Crumple, crumple, crumple. Let me click the lights on for you. I crumple up my mirror here. And are you going to be able to see yourself in it? Can you see yourself? You can't see yourself in this, can you? Why not? Because all the light's bouncing off from weird angles. Yeah, it's like, well, yeah, that's diffuse reflection. Diffuse reflection is the light goes everywhere. It's like playing wall ball outside my classroom. If I got all those 6th graders outside and they all throw a ball straight at that wall, remember the wall outside my room? And they all throw it straight at the wall, all parallel. Are they going to bounce off parallel? It's a bumpy wall. It's called split face block. All right, that split face block, when all those balls hit, it's going to hit and then go jumble everywhere. And then that's what happens with diffuse. When the light hits this jacket, the light goes everywhere. Now her jacket reflects light. This rock out here, this is Mono Lake, it reflects light. Her hair reflects light. Her face reflects light. If you were sitting there in your desk, you reflect light. That's how I can see you. But if you reflect light and a mirror reflects light, you reflect light and a mirror reflects light, can I use you as a mirror? I can't use you as a mirror, can I? But you reflect light. So wait, what's the difference? Your face has texture. Just like that crumpled up aluminum foil. It has texture. Your face has texture. If I stuck your face under a microscope, you'd say, don't do that. Don't do that. You'll see all my imperfections because you know your face has texture. Just like the wall outside has texture, so the light hits and it can't bounce off regular. It bounces off all diffused. So those are the two main broad categories of reflection, is regular and diffuse. So everything in this picture is reflecting light. The jacket, the rocks, the branches down there. Well, the atmosphere is not so much reflecting light. We could argue in some ways that it is. But, okay. It's diffuse reflection. A metal frying pan would be regular reflection. And Let's see, your white piece of paper would be diffuse reflection because it's got all that texture in it. Your ink absorbs the light and the paper reflects the light, and so you can see between what you've written and the paper itself. All right. Let's get to some cool examples of reflection. Total internal reflection. Total internal reflection. Let's break it down to the 3 words. Last word first, reflection. Something's going to reflect. Where? Inside. How much? All of it. All right. Imagine this. You ever wonder if I had a room full of mirrors and I got inside that room full of mirrors, all mirrors, and I shine a flashlight and shut the door real quick? Would the light bounce around in there forever? Bing, 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 bing. I come back in a million years, whoop, and the light comes out? Yes, it should work. If everything was a perfect mirror in there, perfect, the light would just bounce forever. The energy is conserved. It can't just fade away. As long as it didn't get absorbed into some weird imperfection in the mirror, it would go forever. Bing, 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 bing. That would be total internal reflection. Something's reflecting inside all of it. So there are things that do this that are super cool. Here, watch this. Let's show you an example. Here it is. All right, laser. Laser beam. Laser, see the laser? Here, look at this. It's pretty neat. You can't see. Let's turn off the lights all the way here. All right. Now if I shoot you see the laser. It's pretty bright there. If I point it sideways, maybe you see the dust. Here, look. The light has to hit something, first of all, for you to see it. Something to reflect off of. None of it slip on the floor. This is why they put fog inside of, places where you dance, so you can see the light beam. Okay. Now I got this laser. But look here. Let me keep that off for a second, actually. Turn this one on. All right. Got this plastic. It's like a lollipop here, all right, and my laser. If I shine this laser, look at that. Did you look at that? How neat is that? Huh? All right. The light went around and around and whoop, boop, throughout the end. It made turns. How did it go around? Isn't light supposed to travel straight, but I made a turn. I can also do it this way. I can point it this way. Boop. Look, it's coming at you now. It goes around and around and around. I got this toy. Here, going. Let's turn off this light now. You can get these things at, I don't know, sporting events where here's the lights making a turn here. Look at this. If I take my laser, I'm going to take it, I'm probably pretty dark right now, but I point it, I turn the plastic, and the light makes a complete horseshoe bend all the way around. All right. So, how do I get this back on? Boom. So, total internal reflection is that light sometimes goes into a mirrored passageway and it keeps getting bounced around and on it goes. Plastic can do this. And water can do it as well. This is pretty neat. Look at this fish. This fish is trying to see out of the lake. You ever gone to the bottom of a pool and looked up? You see something like this. You're underwater and you're looking up and you just see a reflection of the bottom. You see a reflection you can't see out. If there could be a whole army of zombies outside, but you can't see out because you see a mirror on the top. The light can't get through the surface of the water except if it's at a hard enough angle. Then it can break out. So the hard angle here is this 96-degree angle. I think 90 degrees. 90 and then a little bit more. When you're at the bottom of a pool, next time, sink to the bottom and look up and you will see a circle of outside. Everything outside that circle is mirrored. is mirror bottom. The light is reflecting totally inside. Total, internal, in the water, reflection. So let's see some pictures here. This is a painting, but you can see the artist has painted in the reflection from underwater and then the part that you can see that the light can break through. Sometimes light does hit and can get out if it hits at a straight enough angle. But outside that 96 degrees, it's trapped. You can kind of see out the water here a little bit. You can see in this drawing here how the light bounces until it hits the hard end, and then it can smack through. So that's the idea of fiber optics. Fiber optics is super cool because if I can send, where's the remote? So here's the video projector remote. This shoots light. Imagine this. You buy a TV. You buy the TV and you put it in New York. You're in Las Vegas. I have, let's pretend, 2,000 miles of this plastic. I put one end pointed at the TV and the other end by my remote, my TV remote. If I fire my remote in Las Vegas at that plastic, and I have the 2,000 miles of this going through desert, over the Rockies, through the plains, over the Appalachians to New York, will it turn on the TV? Do you think it will? It should. Because why? The light got all the way to the TV. And how long would it take for that light to get there? Speed of light. How much electricity did it cost for me to send that burst of light all the way to New York? Was this all electrical wire where I had to push a lot of electrons? The light was 100%. It made the whole journey. Light energy is conserved. That light got reflected. How much of it? All of it. Total internal reflection. Made it all the way down there in a heartbeat. Next question. I got a TV over there. I have a friend in New York says, I want to put a TV in Las Vegas. So he shoots his remote to my TV in Las Vegas. He could turn on my TV. So what? Do we have to take turns? Do I have to let my light get through first and then he can shoot his light through? Or can we do it at the same time? We can do it at the same time. Because light is energy, and energy doesn't take up space. Matter takes up space. It has mass, takes up space. Not so energy. Energy can pass right through the other energy. My flashlight can pass right through your flashlight. Like it wasn't even there. I can send a signal this way and that way at the same time. This is fiber optics. This is how you can communicate. They have these cables going underneath the oceans. Let me ask you this. How much light can I send at the same time in the same direction? As long as they can be pulled out and separated on the other end, I can send unlimited amounts. It's not going to get overloaded and overheat with light. It's not going to do that. I could code one information using infrared light. I could use visible light. I could use blue light for one signal and green light for another. I can encrypt it one way and encrypt it another way another. I can have unlimited light inside of that fiber optic cable. As long as I can decode it on the other end and separate it out. Why not? So this is fiber optics, and it moves at the speed of light, wastes very little energy. I don't need to put extra strong batteries in there for it. This is fiber optics. It not only can be used, it is used. So this total internal reflection is a big deal. This is the only picture of a polar bear I could find. He's probably eating the photographer, something. But okay, polar bear, their hair is fiber optic. I need to add a picture to this. I took a picture because I was near a stuffed polar bear over. We went to Alaska this last summer, and they had a stuffed polar bear, and their hair is fiber optic. I forgot to put the picture, but I did take the picture. But their hair directs light to their skin, and guess what color their skin is? If you ever shaved a polar bear? Don't. He did. It's black skin, so the light hits their white fur, helps them be camouflaged. But then that light goes into their fur and warms the black skin that they have, keeping them a little extra layer of warmth then. So it's just a well-designed creature.